Okay, ever looked at a straw in a glass of water
Yeah.
and thought it looked, well, bent? Or wondered what gives diamonds that incredible sparkle?
Right, those everyday things, they actually hint at something really fundamental about how light works.
Exactly. And that's what we're diving into today. The way light bends and sometimes gets trapped. We're talking refraction and total internal reflection.
And this deep dive is for you, the learner. We know you're curious about these things, and our mission here is really to unpack the core ideas.
We want to make it clear, right? Not overwhelming.
Precisely. We'll be using insights from our source material, specifically a chapter focused on refraction at plane surfaces, to pull out the key principles and maybe some surprising facts.
And guiding us through this, as always, is our expert. So let's jump in. Refraction, it's more than just that bent straw illusion, yeah? What's the basic idea?
It is. Simply put, refraction is just the change in direction of a light ray. It happens when light goes from one transparent material or medium into another.
So it happens right at the boundary?
Exactly, it's a surface phenomenon, right where the two media meet.
Okay, but why does it change direction? What actually makes the light bend?
The key is the speed of light. It changes speed when it moves between materials that have different optical densities.
Densities.
Yeah, think of light moving through air, then hitting water. Water is optically denser than air.
So it slows down in the water.
It does. And conversely, when it goes from water back into air, it speeds up.
Now, our source makes this interesting point about optical density versus like regular mass density.
Yeah.
Kerosene floats on water, so it's less dense mass-wise.
That it's optically denser.
Right. Why is that distinction important?
It's crucial because it tells us that how much a material slows light isn't just about how heavy or packed it is, it's a different property. And this difference explains some weird optical effects you see, things that wouldn't make sense if you only thought about mass density.
Okay, got it. So back to the bending. How does the speed change cause the bend?
Well, imagine light hitting the boundary at an angle. One side of the beam enters the new medium first and changes speed before the other side.
Like marchers hitting mud.
Kinda, yeah. That difference causes the whole wavefront to pivot, to change direction. If it's going from a rarer medium, like air, to a denser one, like water or glass, it slows down and bends towards the normal.
The normal being that line perpendicular to the surface.
Exactly. And if it's going the other way, from denser to rarer, it speeds up and bends away from the normal.
Makes sense. Is there a time it doesn't bend?
Yes, absolutely. If the light hits the surface straight on, perpendicularly what we call normal incidence or zero angle of incidence, its speed still changes.
If the densities are different.
Right, but its direction doesn't change. It just goes straight through, albeit faster or slower.
Straight in, straight out.
Yep.
Okay. Now, the source brings up Snell's laws. Sounds like the official rules for this bending. What are they?
They really are the rules. Snell's laws give us a mathematical way to describe refraction. The first law is pretty straightforward. It just says the incoming ray, the bent ray, and the normal line all lie flat in the same plane. It's a 2D thing happening at the surface.
Nice and tidy. What's the second law?
The second law is the really powerful one. It says that if you take the sine of the angle of incidence, that's the angle the incoming light makes with the normal, call it I, and divide it by the sine of the angle of refraction, the angle the bent light makes with the normal, call it R, that ratio is always constant for any two given materials.
Constant ratio.
Yep.
Okay.
We write it as fractions there, and that constant value is the refractive index of the second medium relative to the first. We often write it as 1 mu 2.
Refractive index. That term comes up a lot. So what is it, basically?
Fundamentally, refractive index, usually symbolized by mudr, the Greek letter mu, is a measure of how much a substance slows down light compared to how fast light travels in a vacuum.
So the absolute refractive index.
Right, that's the ratio of the speed of light in a vacuum, c, to the speed of light in the medium, v. So 1 mu, cv.
Okay, so a higher refractive index means light travels slower in that material. The source table shows vacuum and air are almost 1.
Very close, yeah.
Water's 1.33, glass around 1.5, and then diamond is way up at 2.41. That's a big difference.
It's a huge difference, and that high refractive index is, well, a major reason diamonds sparkle so much. It means light slows way down inside and bends very sharply.
So any refractive index bigger than 1 just means light is slower there than in a vacuum.
Exactly. For diamond, that 2.41 means light travels 2.41 times faster in a vacuum or air than it does inside the diamond.
When light refracts, we've got speed changing, direction changing.
Yeah.
What about other light properties like wavelength?
Frequency?
Excellent question. Speed changes, we know that. The frequency of the light, however, which is what determines its color, that's set by the original source. It doesn't change during refraction.
Frequency stays the same.
But speed, frequency, and wavelength are linked. Speed equals frequency times wavelength. So if speed changes and frequency f stays the same, then the wavelength must change too.
Precisely. In a denser medium where speed decreases, the wavelength gets shorter. The new wavelength lambda is the original wavelength lambda divided by the refractive index and mu. So lambda, lambda, mu.
And in a rarer medium, wavelength increases along with speed.
Got it.
So color stays the same, but the wave itself gets sort of compressed or stretched out.
That's a good way to visualize it.
What determines a material's refractive index then? Is it just inherent to the material?
It's primarily the nature of the medium. Yes, it's optical density. Like we saw, glass is optically denser than water, so it has a higher refractive index.
But other things affect it too.
They do. Physical conditions matter, especially temperature. Generally, if you heat a substance up, its refractive index tends to decrease slightly.
Interesting.
And crucially, the color or wavelength of the light itself matters. Refractive index isn't quite the same for all colors. It's typically higher for shorter wavelengths like violet light and lower for longer wavelengths like red light.
So a mu for violet is greater than a mu for red.
Exactly, move and mirror. And that's why prisms work. They split white light because each color bends by a slightly different amount due to the slightly different refractive index for each wavelength.
Wow, okay. It's all connected. The chapter also talks about the principle of reversibility. What's that about?
It's a really neat idea. It basically says light doesn't care which way it's going along a path. If light can travel from point A to point B, going through various reflections and refractions, then if you shine light back from B, aiming it along the exact path it arrived on, it will follow that same path perfectly back to A.
So it retraces its steps.
Perfectly. This means if you know the refractive index going from medium 1 to medium 2, the index going from 2 back to 1 is just its reciprocal.
So air to glass is 1.5.
Then glass to air is 1 divided by 1.5, which is about 0.67. It's a very useful relationship in optics.
Like light has a perfect path memory. Now, besides hitting the surface dead on, are there other times light passes through without bending?
Yes, one other key situation. We mentioned normal incidence angle equals 0 circle, where it goes straight through even if the speed changes.
Right.
The other time is if the two media happen to have the exact same refractive index. Mu and dollar equals mu2 too.
So if the optical density doesn't actually change at the boundary?
Then the light doesn't see a boundary, effectively. Its speed doesn't change, so its direction doesn't change either, no matter the angle it hits at. It just keeps going straight.
That makes sense. No change, no bend. Okay, let's talk about that classic experiment. The rectangular glass block. What happens there?
Right, the glass block. Light actually refracts twice. First, when it enters the glass from the air.
It bends towards the normal because glass is denser.
Correct. Then, when it leaves the glass on the other side going back into air.
It bends away from the normal, speeding up again.
Exactly. And because the entry and exit surfaces of the block are parallel, the amount it bends away on exiting is exactly the same as the amount it bent towards on entering.
So the final ray comes out parallel to the original ray.
Yes, but shifted sideways. It doesn't continue along the original line. It's displaced laterally. We call this shift lateral displacement.
Lateral displacement. Okay. What makes that shift bigger or smaller?
3 main things. First, the thickness of the glass block. Thicker block, more shift.
Makes sense.
Second, the angle of incidence. The steeper the angle you send the light in at, the greater the sideways shift.
Okay.
And third, the refractive index of the glass itself. Higher refractive index, more bending, so more lateral displacement. And since refractive index depends slightly on color.
Different colors get shifted slightly different amounts.
They do, yes. Usually a very small effect for a standard block, but it's there.
And if you have a thick piece of glass, especially a mirror with silvering on the back, the source says you can see multiple images. How does that work?
Yes. When light hits, say, a thick mirror, a little bit reflects off the very front surface of the glass. That's usually a faint image. Most light goes into the glass, refracts, hits the silvered back surface, and reflects strongly. Then it comes back out through the front, refracting again. That reflection off the silvering gives you the main, brightest image.
But there are others.
Yes, because some of that light reflecting off the back surface can actually reflect again off the inner side of the front surface, get trapped, bouncing back and forth inside the glass a few times before some of it leaks back out.
Multiple internal bounces.
Exactly. Each time some light escapes, it forms another progressively fainter virtual image. But that second image, from the first strong reflection off the silver ring, is by far the brightest.
Fascinating how complex it gets inside even a simple piece of glass. Okay, let's shift gears completely now. From bending to trapping. Total internal reflection. What's the setup for that?
Total internal reflection, or TIR, it's a really cool phenomenon. It can only happen when light is trying to go from an optically denser medium into an optically rarer one.
So like from water into air or glass into air.
Exactly. Imagine you're underwater with a flashlight, shining it up towards the surface. If you shine it straight up, it goes straight out.
Right, normal incidence.
But as you angle the beam more, it refracts, bending away from the normal in the air. The angle in the air gets bigger faster than the angle you're shining it at in the water.
Okay, the refracted angle increases.
It does, and you eventually reach a specific angle of incidence in the water. We call this the critical angle, where the refracted ray in the air bends so much it just skims right along the surface at 90 degrees to the normal.
The critical angle.
Yeah.
So that's the limit for light getting out.
It's the boundary case. Now, what happens if you increase your angle in the water just a tiny bit more than that critical angle?
Does it not get out at all?
Exactly. If the angle of incidence in the denser medium is greater than the critical angle, no light refracts into the rarer medium. Zero. All of it, 100%, reflects back down into the denser medium.
Wow. Total reflection.
Total internal reflection. It's like the surface suddenly becomes a perfect mirror, but only for light coming from the denser side at those steep angles.
That's trapped inside. How is that critical angle connected to the refractive index we talked about earlier?
There's a direct mathematical link. The sine of the critical angle, sin C, is equal to the reciprocal of the refractive index of the denser medium relative to the rarer one.
So sin C1 mu. Assuming the rarer medium is air or vacuum with 1 at approx to 1.
Precisely. Or you can rearrange it. Then refractive inverse sin C. So if you know the refractive index, you can calculate the critical angle and vice versa.
The source gives some values. Glass air critical angle is around 42 degrees, water air about 49 degrees, and diamond air only about 25 degrees.
Yes, that 25 degrees for diamond is incredibly small.
And that must be key to its sparkle, right? Light gets in, but once inside, it hits an internal surface. If the angle is more than 25 degrees, which is very likely,
it undergoes TIR. It bounces around inside, reflecting internally multiple times before it finds a facet it can exit through, often splitting into colors as it does. That's what creates the fire and brilliance.
Amazing. Does the critical angle also depend on color and temperature, like the refractive index does?
It does, because it's directly related to the refractive index, since refractive index is slightly higher for violet light than red light.
The critical angle for violet must be slightly smaller than for red.
Correct. And since higher temperature usually means slightly lower refractive index,
The critical angle would slightly increase with temperature.
generally, yes. These effects are usually subtle, but measurable.
Okay, so to recap TIR, light must go from denser to rarer, and the angle of incidence in the denser medium must be greater than the critical angle.
Those are the two essential conditions.
What makes TIR so special compared to, say, reflection off a regular mirror?
The biggest difference is efficiency. A normal mirror, even a very good one, always absorbs a little bit of light and maybe transmits a tiny bit. Reflection isn't quite 100%. But total internal reflection is 100% reflection, at least theoretically. No light energy is lost to refraction or absorption at the boundary during TIR. All of it gets reflected back.
That 100% reflection sounds super useful. The chapter talks about applications, like total reflecting prisms. How do those work?
They're clever devices. Often they're right-angled prisms made of glass, shaped like a 45-90-45-degree triangle.
Right.
If light enters one of the shorter faces perpendicularly, it travels straight to the hypotenuse, the longest face. It hits that face at an angle of 45 degrees.
And 45 degrees is greater than the critical angle for glass air, which is about 42 degrees.
Exactly. So TIR occurs. The light reflects off the hypotenuse and gets deviated by 90 degrees, exiting through the other short face.
And that's used in periscopes to see around corners.
Precisely. Periscopes use prisms like this, or pairs of them, to redirect the line of sight.
What about binoculars and cameras? The source mentions using prisms there too.
Yes, often pairs of prisms, like prisms, are used in binoculars. Light enters, undergoes 2 TIRs, often deviating the path by 180 degrees in total.
Turning the light path back on itself.
Right. This serves 2 purposes. It folds the light path, allowing the binoculars to be shorter and more compact, and it also inverts the image, which is necessary because the objective lenses initially create an upside-down image. The prisms flip it right way up.
Clever. And slide projectors, too.
Sometimes, yes. A prism using TIR can be used to erect the image from an inverted slide so it appears upright on the screen.
And these prisms are generally better than using mirrors for these jobs. Why?
Two main reasons. First, the image brightness. That 100% reflection from TIR means the image is brighter than what you'd get from a mirror, which always loses some light.
Okay, brighter image.
Second, durability. The reflecting surface in TIR is just the internal glass surface. It doesn't tarnish or degrade like the silvering on the back of a mirror can over time, so the image quality stays consistently high.
Makes sense. The chapter also mentions other prism shapes, like equilateral or 30, 60, 90 prisms, and how TIR might or might not happen. It seems pretty dependent on the angles.
Absolutely. The geometry is key. In an equilateral prism, if light hits a face normally, it then hits the next face at 60 degrees. Since 60 is greater than 42, TIR will occur.
Okay.
With a 30, 60, 90 prism, it's more complex. Depending on how light enters, it might hit an internal surface at an angle less than the critical angle, so it just refracts out, or it might hit at an angle greater than C, causing TIR. You can get different deviations depending on the entry angle and which face the light hits.
So it's all about whether that angle of incidence inside the glass exceeds the critical angle for that specific interface.
That's the deciding factor.
Okay, finally, let's talk about some everyday consequences of TIR. Mirages, the shimmering water on hot roads. How does TIR explain that?
Mirages are a fantastic natural example. On a really hot day, the air right near the road surface is much hotter than the air just above it.
Hotter air is less dense, optically rarer.
Exactly. So you have layers of air with the rarest, hottest air at the bottom and progressively denser, cooler air above. Light from the sky coming down towards the road at a shallow angle passes from denser, cooler air towards rarer, hotter air.
Denser to rarer.
And if the angle it hits those hot layers at is greater than the critical angle for that air boundary.
Total internal reflection.
Right. The light from the sky reflects off that hot air layer near the ground and comes up to your eye. Your brain assumes light travels in straight lines, so it looks like the light is coming from the ground.
Like a reflection in a puddle of water.
Precisely. You're seeing the sky reflected by the hot air.
That's brilliant. What about the other examples? An empty test tube in water looking shiny.
Same principle. You have light traveling in the water, denser, hitting the air trapped inside the test tube, rarer. If it hits at an angle greater than the water-air critical angle, about 49 degrees, TIR occurs, and the surface looks like a silvery mirror.
And cracks in glass sparkling.
Again, a crack usually means there's a thin layer of air trapped between the glass surfaces. Light traveling in the glass hits this air gap. Glass to air, denser to rarer, if the angle is right. TIR makes the crack look bright.
And back to diamonds. High refractive index, small critical angle.
Means lots and lots of TIR inside, trapping light and making it bounce around before escaping, creating that sparkle.
And we can't finish without mentioning optical fibers. They're everywhere now, carrying internet data. How does TIR make them work?
Optical fibers are basically very thin strands of high-purity glass or plastic surrounded by another layer called cladding, which has a slightly lower refractive index.
Okay, so a core and a cladding.
Right. Light is shown into one end of the core. It travels down and hits the boundary between the core, denser, and the cladding, rarer. Because the fiber is so thin, the light always hits this boundary at a very shallow angle, much greater than the critical angle.
So it undergoes TIR every time it hits the edge.
Every single time. It just bounces perfectly off the inside surface, reflecting its way down the fiber for potentially kilometers, with almost no loss of light intensity.
Incredible. Carrying signals as pulses of light.
That's the basis of modern high-speed communication.
Wow. So from bent straws to the internet backbone, it really comes down to these two core ideas, refraction and total internal reflection. We had to sum up the absolute key takeaways.
I'd say, 1, refraction is light bending because its speed changes between materials of different optical densities. The refractive index tells you how much. 2, when light goes from denser to rarer, there's a critical angle.
Yeah.
If the angle of incidence is greater than C, you get total internal reflection, 100% reflection back into the denser medium.
And 3,
these aren't just lab concepts. They explain mirages, diamond sparkle, how prisms work, and the technology behind things like optical fibers. They shape how we see the world and how we communicate.
It really is amazing how these fundamental rules of light are woven into both natural phenomena and our most advanced technologies. So next time you see any of these effects, maybe take a second to appreciate the physics. And here's something to think about. How else might we use these principles of light bending and traveling in the future? What other secrets of nature or technological leaps might depend on understanding refraction and TIR even better?
That is a great question to ponder. Thanks, everyone, especially you, the learner, for joining us on this deep dive into the fascinating world of light.